Okay, welcome back, everybody. This one will be the meat and potatoes of this first set of mini lectures. This is on Bernoulli's equation. So let's hop into it. Okay, Bernoulli's equation. What is Bernoulli's equation? Bernoulli's equation is an equation which basically answers the question, how does energy change in a fluid system in dynamic equilibrium? Typo, let's go. What does that mean? So first off, what is dynamic equilibrium? So dynamic equilibrium, I'll write just a word for it first, which is that if I take a point, or an example first, which is that if I take a point in a fluid system in dynamic equilibrium, say I've got current flowing to the right here. I'll mark current in red. That'll be fun. There we go. Say I've got current flowing to the right here. If I look at a point in a fluid circuit in dynamic equilibrium, what that means is that the current that this point would observe passing by at any given time, so if I just like were on this point and I was looking around at the current around me, I'd observe that the current is constant in time. Current is constant in time. So another way of saying that is that the current at any given point is unchanging. The current is the same number throughout time. So it doesn't mean that that just like no fluid is moving. So equilibrium is not the same as nothing moving. It just means that the rate of current flow, the rate of fluid flow, sorry, the current is unchanging. Okay, so that's the basic question that the Bernoulli equation answers. It can be used, bootstrapping off of that, bootstrapping off of that knowledge of energy, it can be used to determine all kinds of things, like the pressure in a system, or the speed of the fluid, or it can be used to determine like the density of the fluid. So you can get a lot of information out of the Bernoulli equation. Um, yeah. Okay. So this is its form. It has 3 terms on the left side, 2 terms on the right side. I want to talk briefly about this little delta here. So each of these deltas correspond to some notion of final minus initial. So delta still means delta of some quantity. I'll call it delta of pressure. Still means final minus initial. But for the sake of convenience, we are always going to set our final point to be further downstream. So as a kind of like pretext to that, these initial and final points are not actually points in time as they often were in 7a, but are instead points in space, like positions along a fluid system, like a pipe. So if I knew the pressure at this first point, and I knew the pressure at this final point, or this final little area here, I could calculate the change in pressure between those 2 points as pressure final minus pressure initial. Okay, that's delta. Cool. So I want to talk a little bit about why it has this form, like what it means. We also call this thing the energy density equation. So what I'm going to do is let's write it down, and then we'll break it into its terms. So delta P, pressure, plus rho G delta Y, plus 1/2 rho delta of V squared equals E pump per volume minus I times R. Okay, so let's look at the left side first. This first term I call the pressure component, or the pressure head. Head is just a word that we use to mean energy density. So pressure head for this first pressure term. We talked about pressure in the last video. It's like related to how hard the particles are trying to push on the walls. The second one I call the gravitational potential energy head, or the gravitational potential energy density, or the gravitational head, or gravity head. And the last one is 1/2 times a density, which is kind of like a mass, times a speed squared. So this is going to turn out to be a kinetic energy density, or a kinetic head. Okay, cool. So that's the left-hand side. I can think a little bit about why that is, like why it has that form, if I imagine a pipe that slants downward like this with some fluid flowing in it, and I imagine just looking at a little chunk of that fluid. So I imagine this little chunk of fluid as it's moving along in this pipe. A little chunk of fluid as it moves along in the pipe. Okay, so as it falls, it's going to lose energy mgh, right? mgh, or mg delta y, to put it a little more suggestively. So that's a potential energy change. And if I think about this now, not in terms of like an individual chunk, but as like an energy per volume, that means that my gravity head would be mg delta y per unit volume, which is just going to be a mass per volume is my rho, that's my density. So it's rho times g delta y. So this refers to the change in gravitational potential energy per unit volume of the fluid moving down. Okay. Similarly, for kinetic energy, this guy here, we've got, if I look at just this little block, that little block would have kinetic energy change of 1/2 m times delta of v squared quantity. So just that little block would have a change in kinetic energy of 1/2 m delta v squared. But if I think about it now in terms of not the block, but the whole, or the energy per unit volume, I can divide that by a unit volume. And again, my mass per volume becomes a rho. It becomes a density, a mass density. So my kinetic energy head, or my kinetic head, becomes 1/2 rho delta of quantity v squared. Notice it's delta of quantity v squared. So like that means that if I have a v final and a v initial, delta of v squared is v final squared minus v initial squared. It is not v final minus v initial squared. Common mistake. Be careful. Okay, so now I want to move on to a short little example that hopefully demonstrates how we might use this equation. So let's go up. Let's go over here, let's say. Okay, so let's say that we have some fluid system, let's say it's a pipe, just for fun. Let's say we have a pipe, does some squiggles, maybe it gets wide in some areas, gets narrow in some other areas, whatever. It's got various areas, various fluid speeds, various heights. If there's no pump and there's no resistance, then the right-hand side of the equation is 0. And what that tells me is that the differences in these terms must eventually cancel each other out to equal 0. So if I pick any 2 points, say some initial point here, and some final point, I don't know, say over here, wherever, just any arbitrary collection of 2 points, and I calculate the differences in pressure, and the difference in the gravity head, and the difference in the kinetic head, if I sum up all those differences, they're going to add up to 0. Another way to say that is that the energy density in a fluid system, in a pump-free frictionless system, is the same throughout the system. I could calculate the energy density at any one of these points, and the sum of individual components of the energy density, is going to sum up to the same number. Now it changes when we throw in a resistive pipe or a pump. Okay, so let's look at the right-hand side for a second. Okay, so the right-hand side of the equation has 2 more terms. We have a pump turn, the energy that a pump adds per volume. I'll just call it pump addition. I'll just call it pump energy density. And we have dissipation. So this is a resistance times the current. We can think of it as basically the energy that the fluid loses by bumping into things and losing energy as heat. So, for example, if you have a rough pipe or if you have a fluid that has a lot of internal friction, then you might have some resistance. You might have some energy lost as heat. So this is a resistance term. Okay. So pumps, again, act as sources of energy density, and resistance acts as a loss of energy density in the form of heat. Maybe it escapes through the walls of the pipe. So one place you might see these terms is in the context of a circuit with a pump. So if we had a circuit that had a pump in it, here we go. If I have a pump between 2 points, here's an initial point, here's a final point, this is when I would include my pump term, E pump per volume. Similarly, if I'm considering the difference between two regions that have a rough pipe or a region that's known to be resistive in between them, here's some pipe roughness here. And again, if I'm considering an initial point and a final point that include the pump or that include the resistive area between them, that's another time when I would include this term. It means that over that area, we are losing some energy to resistance. We're losing some energy density to resistance. Or in the case of the pump, between the initial and the final point, we're gaining some energy. So the pump is dumping in some energy. Those are periods where you would use the right-hand side. Okay. I think those are the basics for this video. We will come back with continuity and then do some intuition builders.